So welcome to today's seminar. Who will tell us something about Ramsey properties of ultrafilters.
Okay, the title might be scary for someone who's not into ultrafilters, so a better title would be Ultrafilters in Ramsey's theorem, which I suppose should be closer to home for you. First of all, let us converge to the common ground, because I suppose naively you are all graph theorists or computer scientists. So we need to reach common ground with set theory, which is what ultrafilters are. So let me start by asking if everybody knows what an ultrafilter is, and if not, if anybody knows what an ultrafilter is. Okay, so that's where we start. Okay, so let me start by defining what a filter is. The notion is very natural. It is a way to capture an idea of a large subset. A filter on a set is a collection of large subsets. Large in what sense? So definition. So you have a collection of subsets of some ground set X, and you say that this collection is a filter if the collection consists of large subsets in this sense. First of all, the empty set is not there, because that's not large. And the entire set is there, because the entire set is a large subset of it. Second, if a set is there, then any larger set is also there. So if A is an F and B is a superset of A, then B is also large. And thirdly, if two sets are there in the collection, then the intersection is also in the collection. So it is closed under intersections, closed under superset. The entire set is there and the empty set is not there. A naive picture for that, this is the collection of all the subsets, the power set. This is the empty, this is the entire set. And these are the larger ones. Let's say a filter is something like that on the Boolean algebra of subsets. There's a dual notion, completely dual to that, which is that of an ideal. Let me just shortly mention that if your family forms a filter, an example first. Example, all the subsets of the integers. This is generally defined on a set, but I will mostly be talking about sets of integers because we're heading towards Ramsey theorem. So the collection of those subsets of the integers which only have a finite complement. So subsets containing almost everything. Those are large because this is trivial, and if two sets have a finite complement, then the intersection still has a finite complement. A dual notion for that is the notion of an ideal, on some set generally, which is exactly the opposite. The empty set is there, and the entire set, ideal. The entire set is not. If a set is there, then every subset is also there. So now it is closed under subsets. And if two sets are small, then the union is still small. These notions are completely dual. Namely, if your collection forms a filter, then the complements of those form an ideal. You can see this is completely dual. The dual ideal for that filter will be what people call fin, the collection of all subsets that are finite. That's obviously an ideal, because the empty set is ideal. If this set is infinite, this is only interesting for infinite sets, obviously. If this is finite and this is finite, if two of them are finite, the union is still finite. So this is the basic example. You will meet ideals all over mathematics if you look for them. For example, the sets of Lebesgue measure 0 are an ideal on the real line, etc. You will meet them everywhere in algebra and topology. But we will only concentrate on filters or ideals on the set of integers.
Okay.
Right?
So if I take all subsets that contain 1, that's also a filter.
Yes. That's what's called a trivial filter. In fact, an ultrafilter. That will be the trivial example. Okay, so in my naive picture, In my naive picture, this is the dual ideal, usually marked by a asterisk. You will notice that this notion of largeness or smallness does not decide everything. In this naive picture, these are the large ones. Their complements are the small ones, but there are sets which are neither large, neither small in that regard. Like every infinite subset with an infinite complement is neither small nor large in this notion. So that's the extreme case, an ultrafilter which does decide everything. So definition, if, moreover, this is true for every subset A of the ground set X, either A is in the filter or the complement of A is in the filter. So the picture becomes this. You are either big or you are small. There's nothing in between. If moreover this is true, then F is an ultrafilter. Now, ultrafilters are rather hard to come by. Specifically, as Andrea said, this is an example of an ultrafilter. Take all the subsets of the integers which contain the number 7. That's an ultrafilter, because containing 7 is preserved by all these. You either do or don't contain 7, and this is trivial. So this is a trivial ultrafilter. That's what it's called, trivial ultrafilter. And the question is, of course, are there any others besides the trivial ones? Yes, there's plenty of others if you assume the axiom of choice, but they are not definable in the sense that you cannot write a formula down. That's a homework. That's a nice homework. Write a formula. Write a formula of set theory, meaning the language of set theory. Let's say f of a. That's the formula with one variable, such that if you look at this collection of subsets of the integers which satisfies that, write down some property such as containing 7. Write down such a property such that this is an ultrafilter. Try it. What are you going to do? Are the even numbers or the odd numbers are going to be in an ultrafilter? How do you decide? But yet, ultrafilters do exist. In fact, there's plenty of them. It's an application of Zorn's lemma. Once you assume axiom of choice in any of its incarnations, there's as many of them as can be. This is the power set of the integers. This is the power set of the power set, namely the family of those families, and there's this many ultrafilters on the set of natural numbers. I'll show how briefly, because the ultrafilters are exactly the maximal filters. Maximal in the sense that they cannot be extended to any larger family. So that's the first lemma of today. It's very easy. A filter, let's say U, a collection of subsets of the integers is an ultrafilter if and only if U is a maximal filter. Maximal meaning it is a filter, but you cannot add any single set to it. Once you add any single extra set to it, you will break these properties. So it is an ultrafilter which cannot be extended. Why is that? That's easy. An ultrafilter has to be maximal, because if not, well, let some other filter be a larger family than U, meaning there is at least one extra set. So let A be the set which is in F, but not in your ultrafilter U, which means A is not in U, which means the complement of A is in U. So the complement of A is in U, but U is extended to F. Well, so the complement of A is also in F, but that's not possible. A is in F, so the complement cannot be there. I didn't say it explicitly, but a set and its complement cannot be together in a filter. They would have a finite intersection. So a ultrafilter has to be maximum, cannot be extended. And the other way around, we are to show that a maximal filter has to be an ultrafilter. Okay, so give me a subset, and I'm to show that either A or the complement of A is in U. So if A is not in U, I have to show that the complement is in U. If this is the case, then you can add the complement of A to the family you have, and it has the finite intersection property, which is what you think it is. If you take finitely many sets from that family, then the finite intersection is still in that family. Why is that? Because if not, well, U has the finite intersection property because it is in a filter, but you have added one extra set that can break it, but it doesn't break it, because if not, what would that mean? That means you have finitely many sets from here, namely, let's say x1 up to, say, xn in U, such that this intersection x1 intersection x2 intersection da 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 up to xn intersection with the complement of A is 0. That's breaking the finite intersection property, but this means exactly the same thing as this intersection being under A. If you are disjoint with the complement of A, you are under A. But these are sets from the filter, and this is a superset, so A is in U. I've started by assuming that A is not in U. So if A is not there, then the complement has to be there. So it is an ultrafilter. So by this easy lemma, ultrafilters are exactly the maximal filters. Now, maximal filters exist. By Zorn's lemma, does everybody know the Zorn's lemma, or does anybody know the Zorn's lemma? Okay, lemma, very old lemma. It is an incarnation of the axiom of choice. Ernest Zorn, 1908, I think, very old. If you have an ordered set, such as here, the filters ordered by inclusion. In general, you have some order, a partially ordered set, with the extra property such that every chain in X has an upper bound. A naive picture again. This is some order. It can be wild. It can branch. It can be something very ugly indeed. But if you take a chain in there, meaning a subset that is ordered linearly, such as this, that's a chain. That's what chain means, a linearly ordered subset. Then there is an upper bound. There's a point in that order such that your entire chain is below that. That's a property of a poset. Every chain has an upper bound. If you have such a poset, then, says Zorn, then for every say X in X, there is a maximal Y in X, which is above your point. So take any point in such a nice order, and there will be a maximal point above it. Now apply this to this possibility. The collection of all filters, I'll not write it down, but let's say this is the collection of all filters on X, and order them by inclusion. That's a poset, and it has this property, because what is the upper bound of the chain of filters? The union. Take the union. A union of a chain of filters is a filter, and that's the upper bound. So yes, it has this property. Weinstein's lemma, which I will not prove, of course. There are maximal filters, and we know that maximal filters are precisely the ultrafilters. In fact, any filter can be extended to an ultrafilter. So that's part one. This exists. There's plenty of it. Try this for real. Try to define an ultrafilter. Being an application of axiom of choice, it shouldn't surprise you. It's a purely existential statement. There's plenty of them, but I haven't showed you a single one. Try to define them. Okay, the main part comes now. I will be using an ultrafilter to prove the Ramsey theorem. Does everybody know the Ramsey theorem? Or do people generally know? Okay, I will state it anyway. It's a graph theoretical statement, if you want to look at it that way, or it's a set theoretical statement. It's about coloring of graphs. I'll probably skip defining the general notions and just say what I need to say for Ramsey. Okay, so theorem. Frank Ramsey, 1930 old theorem, which says for every coloring of the n-tuples of the natural numbers with any finite number of colors, there is a homogeneous set, meaning this. In Hungarian notation, I suppose people from graph theory are familiar with the Hungarian notation. This is what it says, and it means this. Take the n-tuples of the integers and color them with k colors. Formally, that's a mapping from that set into k. A homogeneous set is a set such that if you only take n-tuples from there, they will all have the same color. So, take the set of n-tuples of integers, that's how I denote it, color them by k colors, meaning the set of 0 up to k minus 1. And there is a homogeneous set. There is some homogeneous set subset of the integers such that the coloring on this set of n-tuples C is constant if you only look at the n-tuples from there. Now, this is trivial if the set is allowed to be small, but the statement is there is a large subset A. There's an infinite. That's the point. In this large set, you will find a very large as can be, namely countably infinite, subset such that the coloring is homogeneous on that set of n-tuples. That's the Ramsey theorem. He proved that as a technicality for model theory, but then people realized it's a very strong combinatorial statement. Okay, so let me prove that using ultrafilters. That's the point of this talk, to show how easy it is to prove it once you have an ultrafilter in your hand. Okay, so proof by induction. By induction on n. The starting point is trivial. If n is 1, then it's the pigeonhole principle, right? Such a coloring is a partition. To color the n-tuples with 7 sets is to partition them into 7 pieces by color. So I will be talking about partitions and colorings interchangeably. So by induction on which, n is the size of the tuples. Okay, by induction on n, we'll show that this is the case for all For all k, that makes it at least one color, of course. And at least a one tuple. Okay, so for n equal 1, it's the pigeonhole principle. You have partitioned the one tuples, that is to say, the set of natural numbers, into 7 colors. Well, one of them has to be infinite, obviously. So the induction step. So let C be some coloring of the n plus 1 tuples now into k parts, or with k colors. And so that's what I have to find the homogeneous set for. And let U be a non-trivial ultrafilter on the neutrals. Plenty of those. The guiding idea of what follows is that the ultrafilter has already done all the work for you. It will guide you and it will tell you this is the right color, pick this point. That's your homogeneous set. The U will dictate, it will tell you on a silver platter, you will be given the homogeneous subset. So, okay, so for any, let me keep the notation. Right. Okay, so for any n tuple, now I'm proving for n plus 1 tuples, but for an n tuple, look at this. Look at what color do you get if you extend that n tuple into an n plus 1 tuple by some extra point. So let me denote it like that. These are exactly the, let's say, m, the natural numbers above x, such that if you take the n tuple and you add this extra point, then it becomes an n plus 1 tuple, and that n plus 1 tuple gets the color I in the given color. So I have 5 tuples, and if I add a 6th point, it becomes a 6th tuple, which is blue. And do that for every color and every n tuple. So this is a partition. Then these sets for all the colors is a partition of this set into finitely many parts, namely by color. Now an ultrafilter will pick one of those. Right. I've set it for 2 sets. That was the defining condition. If you have a set and a complement, the ultrafilter will pick exactly one of those. But it's not a matter of 2, it works for 3 also. In general, if you have a set A, which is partitioned into finitely many in your ultrafilter, then exactly one AI will be in the ultrafilter. It will pick for any finite partition, not just a partition into 2 pieces or 3 pieces, works the same way. So this is a partition of this set, which is in the ultrafilter because X is finite, so the complement is in the ultrafilter, which is non-trivial. And I've just partitioned it into finitely many sets. There has to be a single one which the ultrafilter picks. So exactly one CXI is in the ultrafilter. The ultrafilter has picked the color for you now. So define, let's say G for good, to be the single I in K such that C of X and Gx is in U. That's it. The ultrafilter has done the work for you. Do you ask how you are supposed to extend the 5 tuples into 6 tuples so that it behaves nicely? This is the right color. These are the ones you should pick. That's what the ultrafilter has just told you. It's almost done. Just verify that I have a homogeneous set now. Okay, so now I have to show that, I will build, okay, define a set A, probably already the one or the subset of that, okay. Okay, so I will define a subset, an infinite subset A of the naturals by induction. Let me call it let by U. At every step, U will tell you this is the right continuation out of the finitely many. Okay, so start with some arbitrary, let's say the first n numbers, doesn't matter. Oh, that's A n. And I'll be extending it. Now look at all the n tuples from here. So having some, oh, sorry, n is already used for the size of the tuple, right? So aj. So having some aj finite, look at how the n tuples of that set behave in the color. Look at C at the n tuples of this set. By induction, because we're doing induction, by induction you have something that is homogeneous. Sorry, that's finite. Sorry. Right. Right. Look at not the coloring. Look at all the n tuples. Sorry, I'm here. Look at all the n tuples in here. Look at the right color for each of them. So look at the set that we call the C of X and its good G of X. These are all in the ultrafilter, and do that for all the n tuples of what you already have. This is finitely many. This set is finite, so there's finitely many n tuples in there. Look at their corresponding sets in the ultrafilter. That's finitely many sets in the ultrafilter. So the intersection is also in the ultrafilter. So this set is infinite. So pick the next number of this set you are building from that set. That is the right one. That is the right extension of all the tuples you already have. So pick, what was it, aj now, okay, aj plus 1. From there, oh, it's supposed to be named something now. Okay, so cj. That's it. Okay, without the maximum. Look at, oh, just pick the union of everything you already have. That's finitely many. Throw that away and pick a new one from here. This is the key point. The ultrafilter has told you. You already have 100 points. Look at all the 5 tuples of there. There's a single way to extend, to add an extra point so that the 7 tuples, or whatever the next was, will have the right color, the color favored by the ultrafilter. It dictates what you should do. Just do what the ultrafilter tells you. And that's it. In that way, that's an induction in itself. Like start with any, okay, should be n, right? Start with any n numbers and then extend as you should. You get this set of all these A1, A0, A2, etc. That's an infinite set because I'm always choosing something else, something new, besides what I already have. And now I claim, of course, inside here lives the homogeneous subset. So look at the coloring at that set. This has a homogeneous set, let's say H, because by induction for n tuples, we already have that. So some H, a subset of A, which is infinite, such that this is constantly something, some color. Without lots of generality, I will suppose that the right color is the color 0. Of course, it doesn't matter which color it is. Now I'll claim this set also works for the original. Oh, sorry, typo. Not C. C is the original coloring. The G that picks the good color. The good color is the same for everyone, namely 0 points. Now, if you have that, you already have a homogeneous set for the original coloring too, because, well, almost by definition. Well, then H is also homogeneous for C. Why? Because give me any n plus 1 tuple. So give me some, those were x, so these are y's. So that's x plus something else. Some n plus 1 tuple from there, where m is about the maximum of x. This is just notation. Look at an n plus 1 tuple and in the form like n many of those plus the last one. Okay, then look at that. Look at the constant g of x for all those x's, because H is homogeneous with respect to G. Namely, the good color is good for everyone. It is the same color for everyone here. So the coloring of Y is by definition the, how did I call it? Right. So Y construction, this M is in the, what was it, C of X and 0. That's how I'll pick them. That's how the next member, the next continuation was obtained. Like pick the good one. So he's here. So the color of X is 0, sorry, of Y for every Y in H and plus 1 top. That's it. Step back and look at what we had to do. We had to do nothing. We just let the ultrafilter tell us in every step, yeah, this is the right color. Pick this one, pick from here, that's it. And keep doing that, that's it. So that, honestly, that is the point of this lecture. Once you stop being scared of ultrafilters, you have a very strong tool in your hand. Of course, this is entirely non-constructive. So which color was it? What is the set? I don't know. The ultrafilter tells you what the set is, but I cannot define it by a formula. Of course, if you picked, here's the magic mathematical words, right? Let UBL. Okay, which one? I don't know. Pick one. I'm saying pick an ultrafilter as if you can pick an ultrafilter, but take anyone. A different ultrafilter will, of course, like some other color and will dictate some other set, possibly. I don't know which it is, but I know it is homogeneous. It's a purely existential statement as is to be supposed from something that only exists by an existential statement. Yes, ultrafilters exist, so homogeneous sets exist. That's it. Go home. You have. Okay, how much time did I kill with that?
7 minutes.
Okay. So this is the proof of the Ramsey theorem using ultrafilters. Now there's obvious questions and obvious generalizations for that. We have proved that the set, this is the cardinality of the naturals if you're not into infinite cardinality. We have shown this. Again, for a countable set, of course, the identity of the set of naturals plays no role in that. Any countable set will do, same argument. So in a countable set, if you color the n tuples with k colors, you will find an infinite subset which is homogeneous with respect to that coloring. The obvious question is, what about higher cardinalities? Say you have something uncountable, let's restrict that to 2 and 2, the basic example. Can this work for something that is uncountable? The answer is yes, possibly, but the kappa has to be extremely huge, like so big that ZFC does not even prove the existence. The existence is beyond ZFC. That is to say, it is consistent with ZFC that these cardinalities exist, and it is also consistent with ZFC that these cardinalities do not exist. That shouldn't be shocking. Set theory is not complete. There's many combinatorial statements which are not decided, such as these. And another natural generalization, which is the last part, not only, if you strengthen this to want not only an infinite subset like here, but a large infinite subset, that is to say, a set in the filter. The usual notation is this. Meaning, if you color the n tuples, same thing. If you color the n tuples of the integers with k colors, there will be a homogeneous subset which is in the ultrafilter given in advance. So this is called, you can guess once, the Ramsey ultrafilter. This is a very strong combinatorial property of ultrafilters. And the question is, do Ramsey ultrafilters exist which satisfy this strengthening of the Ramsey theorem, the natural strengthening? First, let's look at, what is it, 5 minutes? Let's look at this characterization. An ultrafilter is Ramsey if and only if it is selective, meaning this. For any partition, like example again, this is a partition of the integers into some xn. For any partition of the set of naturals into a disjoint union of some xn's, either one of them is in the ultrafilter, and there's nothing to do. Either some xn is in the filter, or if not, then you have a selector. That's why selective. You have a set in the ultrafilter which picks exactly 1 point from each of them, called a selector. Or there is some, let's say, S in U, such that the intersection of X, which is each of those exactly 1, and this is called a selector. So either one of them is in U, and if not, you have a selector for this partition. Now I say this is exactly the same thing as satisfying this extension of the Ramsey theorem, and the equivalence is quite trivial. From the partition, you get the coloring. Guess how? What's the 2 colors? I give you a partition of omega, and you tell me a coloring of pairs. What should the partition be? The two colors are, you are in the same part or you are in different parts. That's the two colors. For a partition, let's say Xn, let the color of a pair XY be 0 or 1 if X and Y are in Xn, or otherwise for the same n. That's a coloring of pairs. Either the pair is in the same bubble or it is not in the same bubble. If you satisfy this, what does it mean to be homogeneous in the same? That means one of them is in the filter. What does it mean to be homogeneous in the color that is called different? Well, that means all of them are in different parts, meaning if you have a selector. So it's an immediate translation of one into the other. So instead of looking at this property as an extension, as an ultrafilter extension of the Ramsey theorem, you can look at it as a combinatorial statement with respect to partitions. Now, do these exist? Probably that's the closing remark now. From continuum hypothesis, you have to strengthen ZFC. It goes beyond ZFC again, but not much. From continuum hypothesis, Ramsey ultrafilters exist. And again, there's plenty of them, as many as can be, given the infinite cardinality. And another theorem, of course, you guessed it, Ramsey ultrafilters need not exist in other models of set theory. So ultrafilters exist in ZFC, and they do prove the Ramsey theorem. That was part one. Once you go beyond that, you go beyond ZFC, and it becomes quite a strong combinatorial statement. I guess I have to stop here. Okay, so that's it.
Any questions?
Any counterexamples? Yep.
Well, out of the of choice, ultrafilters do exist.
Yes.
Out of continuum hypothesis, Ramsey ultrafilters do exist.
Mm-hmm.
These are only implications, or?
These are only implications. In fact, CH is way too strong. You can go way below CH and still have Ramsey ultrafilters. In fact, there is some work in classifying or stratifying how much of CH you need to get this ultrafilter and that ultrafilter. CH, of course, kills it all because continuum is omega-1 and you get everything, but it's way too strong for that implication. So it doesn't go the other way. Yep.
Is there something weaker than an ultrafilter that exists if you do not assume the action of choice, but similar?
In fact, the existence of ultrafilters is slightly weaker than AC. The theorem that says that ultrafilters do exist, okay, it's called BPI, which means Boolean prime ideal. Prime ideal is the dual of an ultrafilter. We started with filter and ideal being dual. Prime ideal is the dual of a maximal. So this is implied by AC, as I said, but is not as strong as AC. The statement itself is slightly weaker than axiom of choice, but equivalent to some of the other maximality principles that you might know. It is a maximality principle, namely every filter can be extended to a maximal filter, but it is not the full strength of AC. Okay, so I guess the moral is get into ultrafilters. It will solve all your problems, whatever you do. No.
Because there are none, so let's thank the